Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, dear students. Welcome back to this TV Learning Series program. I'm teacher Patrick, and this time I will be with the Senior 6 class in chemistry, and we are still looking at the derivatives of benzene, remember? And our today's lesson is on the chemical properties of phenol. Phenol is one of the properties, one of the derivatives of benzene. And our objective, we just have only two objectives today. We'll explain the structure and reactivity of phenol, and then we'll have to see the effect of substituents on the acidity of the phenol. Structure and reactivity of phenol, that is what we are looking at. I repeat again. And then effect of substituents on the acidity of phenol. Before we look at the reactivity and the acidity of the phenol, let us make a review of the previous lesson where we talked about the uses, we talked about the preparation methods, we talked about the physical properties of phenol. Do we still remember some of these? Two properties of the phenol: the boiling point, the solubility of the phenol. How is the solubility of the phenol compared to that of other alcohols? Remember, phenol, the structure of phenol, you need to always remember the structures. This is the phenol. So it contains an OH, like alcohols. So does it have the same solubility with phenol, with alcohols? The answer is no. We said the solubility is reduced. So when we're talking about this, the physical properties, remember we talk about the boiling point, the melting point. They are slightly higher compared to those of alcohols because of high number of carbon compounds. The solubility is, we have the solubility, we said it is fairly soluble in water. But at high temperatures above 65, it can dissolve in water. The solubility is reduced in water compared to that one of ethanol because of the high carbon content, the non-polar group. So this non-polar group reduces the solubility because that means the van der Waals forces outweigh the hydrogen bonds that are supposed to be formed with the OH. And therefore, that's why the solubility lowers. State any two methods of preparing. We looked at a number of methods. You still remember some of these methods. From one of the methods we said, from magnesium, this is alkyl, this is a Grignard reagent of the benzene. When put into ether, reacted with ether as the solvent, so it will form the intermediate, which will react with water to form the phenol. That is one of the methods that we looked at. So phenol from this Grignard reagent. From benzene diazonium. From benzene, that was the first one. The second one, from benzene diazonium salt. This is a benzene diazonium salt. But we look at these benzene diazonium salts when we are looking at the aniline or phenylamine. So we have not come to the amines, but this is where it comes from. Benzene diazonium chloride. So when it is put in water, this one changes into phenol. So, and some other methods that we looked at. State two uses of phenol. You remember we said phenol is used mainly as disinfectant or antiseptics. Antiseptics, we said they arrest the development and growth of bacteria. Disinfectants and antiseptics that destroy, that reduces the growth and development of the bacteria. They are also used as germicides. They are put in the soap to kill the germs. One of the examples that we looked at is the Dettol. That is a common soap that is used for bathing. And mainly, we said the phenol compounds are used as antiseptic. They are used as antioxidants. Antioxidants, we said, they reduce the damage of the cells. And if they reduce or they delay the damage of the cells, once they delay the damage of the cells, then that means what? And you remember we talked about what damages those cells. We said they are free radicals that are constantly being formed in the body. By what? By some other toxic substances as a result of either pollution or as a result of the food that we may eat, and so many others. So they delay the formation of those free, they reduce those free radicals that are constantly being formed in our bodies, used as antioxidants. So let us continue and look at this is the structure of the phenol. Just have a look at it. What are these ones? What are these ones? So if we look at the structure, I'm just going to redraw that structure. We are talking about the structure of the phenol. On each carbon, so this is an oxygen. This is a high oxygen and hydrogen attached. And remember, on each carbon atom, each corner of this benzene ring, this is a hexagon. I've just made it. Don't think that this one is longer than, I'm just enlarging it to make it more easier to see. So on each corner of the carbon here, you remember we said there is a hydrogen atom. So if there is a hydrogen atom attached on it, this is hydrogen, another hydrogen, another hydrogen, and another hydrogen, like that. So when you look at this carbon here, it has 3 electrons. Electrons that make this bond here. We have this bond, we have this one. So the carbon here is bonded to 3 electrons. Where is another electron? Because carbon has got 4 electrons in the outermost shell. So where is another one? Another one is the one that we are showing here in the p orbital. So there is a p orbital here. Even here the same. There is a p orbital. This is the p orbital. I'm just trying to, this is the p orbital. These are p orbitals. I'm drawing here. I'm just using different colors so that we don't get confused as we are showing what is happening as a result of the delocalization of these electrons. So we have another one there. We have another one there. And then we have another one there. This must be, I have to use green. And another one there. That is how it looks like. So the oxygen here has got the lone pairs. So this oxygen has got the lone pairs. So you'll see the lone pairs here. They are also in the p orbital. These are oxygen with the lone pairs. So there are some lone pairs over there. What happens? So here, these orbitals, when you look at them, as we talked about the structure of the benzene, when you look at these two orbitals, they are laterally pressed, like this. And if they are laterally pressed, you remember we said the distance here is very small, so they tend to overlap. These orbitals, so this orbital overlap with this one here. So they come together and overlap. So when I talk about the overlapping, this is what I mean, like this. So they come together in this form. That is overlapping. Now, this one, when you look at this and this one, they are also laterally placed. And that means that this orbital will overlap with that one. So there is an overlap that goes like this. This one and this one as well, you see what happens? They are also overlapping together because they are laterally placed. So this one will also overlap with that. It overlaps with this one, and then again. So it forms some kind of orbital on the top. It's just a lobe that is formed on the top of the carbon atoms. And then you'll have these lower lobes also overlapping. So you have this lobe overlapping with that, and this one overlapping with this one. This is also overlapping with that, and overlaps in that form, and then it overlaps in this form. So that means we have two lobes. You remember, we mentioned even this one when we were talking about the structure of the benzene. So, but what we are looking at this time around is these electrons here. Because we said there are these electrons here. So these electrons in the p orbital on the oxygen atom tend to move inside. They tend to move. So that means this orbital here is overlapping with another one of the carbon here in the bond. So if this one is overlapping, that means in the same way, this one also overlaps with that. And what does that mean? There is a bond that is formed here. There is like a pi bond that is formed. A pi bond is formed within here. That explains, because of these electrons entering into the ring, it forms like a pi bond. A pi bond is stronger than a single bond. If you remember how the pi bond is formed and the single bond, is that when you look at the single bond, for example, if we have, this is carbon, if we assume these are carbon atom, this is a carbon atom. I'm just trying to show you how that single bond is formed and then comparing. This is a carbon atom and this is another carbon atom. So when these two orbitals come together to share these electrons. So this is these two orbitals which come head to head. When they overlap together, these electrons are held between the carbon atoms, between these two, the nuclei or the nucleus of these two carbon atoms, held these electrons together in a fixed position. Whereas the electrons here, for this and this one to overlap, the distance has to come close. So these carbons have to reduce the distance. And that's why when the distance is reduced, much smaller than this one, that is why a pi bond becomes harder to break in terms of energy bond breaking. So because these orbitals have to come together for a pi bond to be formed, and a pi bond is the next bond formed after a single bond. So this explains why, when you look at this one, this explains why Phenol does not undergo nucleophilic substitution. Does not undergo nucleophilic substitution like aliphatic alcohols do. Why? Because we are saying aliphatic alcohols, if you remember, this is an example of the aliphatic alcohols. When it reacts with, for example, the hydrogen bromide, and this one forms, this is the compound that is formed, CH2, so it forms an alkyl halide. What happened here is that the bromide has substituted. It has substituted. This is a nucleophile. So the bromide is substituting this. So because this one forms a positive charge, the positive charge will be attacked by the bromide, which is a nucleophile. So this positive charge is delocalized. Even the bond here, it becomes very strong because electrons are entering within the ring. They are entering. And therefore, that explains the reason why this phenol does not undergo nucleophilic substitution like the alcohols. Because the bond breaking here, the energy will be very high because of the formation of the pi bond. And two, the positive charge that will be formed on this carbon atom is delocalized within the ring. That is about the structure of the phenol. Now, talking about this also explains the reactivity. Why alcohols are more reactive compared to the phenol. Because we have said the positive charge here, which is formed on the carbon atom, because you remember this one has to be removed. If you remember the positive charge, I can just show you the simple mechanism of what happens. We said OH with the lone pairs. The hydrogen, this hydrogen here will be attacking the OH with the lone pairs here and then forms RCH2 with OH2 plus. So this one breaks, and therefore this will form RCH2 plus. So this one is the one which will be attacked by this nucleophile, the negative charge. So attacking this one, and then eventually you come up with CH2 bromide. So what happens here in the phenol, that positive charge cannot easily form this one here because of the electrons moving inside, and therefore these electrons will tend to stabilize the positive charge here. And therefore that explains why the phenol cannot undergo the same reaction as alcohols, because of the strong double bond that is formed, and two, because the positive charge that is formed on the carbon atom is stabilized by the delocalization pi electron system. Those are two. So we'll go and talk about the structure. This is what I was just trying to explain. So we can talk about the acidity. The acidity is explained by, when you look at the pKa, these are constant values that explains the strength of the acid. pKa is the negative log of Ka. The higher the value of the Ka, the lower the acidity of that compound. Look at this one. This is ethanol. It has 16. Phenol, 9.9. Carbonic acid, 6.5. ethanoic acid 4.8. What did I say? I said the pKa values indicate or tells us the strength of the acid. If the pKa value is big, that means the acidity is low. Higher pKa values indicates lower acidity. So that means ethanol with a high value, it means it is the lowest acidic. And this ethanoic acid with the smallest value of pKa is indicating higher acidity. And this is what we are just going to explain. So phenol, when it reacts with in water, this is phenol, C6H5OH. So in water, it forms C6H5O plus the hydroxonium ions. These are formed because the hydrogen, this phenol, if it is behaving as an acid, means it has the ability to donate the proton. That is why here we have the phenoxide. So what happens here? What makes this phenol somehow acidic? So the OH bond is weaker in phenol than in alcohol. This is because the lone pair of electrons on the oxygen atom becomes associated with delocalized electrons. So what does this mean? That if you look at this negative charge, if this negative charge is formed on this oxygen, and we have said this oxygen has got, it has got the orbitals here in the oxygen, it will also be entering into the benzene ring. So if it enters into the benzene ring, so that means that there is high possibility that this negative charge is not available at a certain time in the solution. And that stabilizes this phenol, the phenoxide ion. This one is called the phenoxide ion. Phenoxide ion. So it is stabilized by the delocalization of the negative charge, which is formed here that enters. And therefore, in the solution at one time. Remember in alcohols, why alcohols are less acidic is that when they react with water, that ethoxide ion that is formed, CH2 with this one and the hydrogen ions, this is localized. It is on the oxygen. It is permanent. It doesn't move. But here, this oxygen, this negative charge, moves inside. So once it is localized here, what does it mean? It means that at any time once this one is formed, so it will attract again the hydrogen ions in the solution. That's why alcohols, aliphatic alcohols, ethanol is neutral compared to the phenol. So it has some acidic properties because the negative charge is stabilized by the delocalization system. That is why phenols react in the oxygen atom. Phenol, this is a very important note that we shouldn't forget, is a weaker acid, and it does not react with sodium carbonate or sodium hydrogen carbonate, unlike carboxylic acids. So this explains, or it can be used to explain the difference in the acidity between the phenol and carboxylic acids. And therefore, it can be used to distinguish phenol and carboxylic acids. So phenol doesn't react with this, but carboxylic acids do. Sodium hydrogen carbonate and sodium carbonate. So the effect of substituents, this is what we are talking about. How does the effect of these substituents affect the acidity? So here, these are electron withdrawing. The electron withdrawing groups. We have, these are examples. What happens? So it means if the electrons are being taken away from it means that the electrons are moving from this oxygen which is here, electrons are moving inside. Once they are moving inside, that means this bond is weakened much further. And therefore, this bond can easily, because the electrons are pulled away from this bond. And if they are pulled away from the bond, it means it can easily break away. So electron withdrawing groups increases the acidity of these phenol compounds. Likewise, electron withdrawing groups those are electron donating. These are electron donating groups. Electron donating groups, not electron withdrawing. I beg your pardon. We have to change this one. This is an error. Electron donating groups. So these are electron donating groups. So if you have electron donating group, these are examples. The alkyl groups, the amine, the hydroxyl, and so on. So they tend to push the electrons within the ring. What happens? That means electrons are now moving away. If you have electron with electron donating group here, it means it pushes the electron. That means it increases the electron density here, and this bond becomes more stronger. So electron withdrawing, electron donating groups reduces the acidity of phenol compounds. So you have to answer this exercise. Arrange the following groups in order of increasing acidity. That means your base, either it is electron withdrawing or electron donating. Electron donating reduces the acidity. Electron withdrawing increases the acidity. So you have to look at the groups that are attached and tell which one is more acidic. The more acidic is the one that withdraws the electron. This is the least. So that is the order. When you are starting, this is the least acidic. And then you can also look at other depending on those groups. So you will have to arrange that one in order and then finish. So I've given you the hint. You remember this is the first one, the least one that you have to start with. The least acidic, then followed by others. I thank you so much for watching and listening. I hope we'll be together in the next lesson. Bye-bye.
Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.